Hello and welcome to Eng Phys 2P04 Lecture 28, the dynamic beam equation. First we're going to derive the dynamic beam equation. Remember that the angle that a beam makes with the horizontal is the first derivative of its transverse position with respect to x. And from our flexion equation, the moment is equal to EI times the curvature, where the curvature is the second derivative of transverse position with respect to x. Then the shear force is the rate of change of moment with respect to x, so it ends up being the third derivative of transverse position with respect to x. Suppose we take some object like this, some little slice of a beam, and then we've got the internal shear force on each side of it, which we'll say is a function of x, and the moment on each side of it. Then the net force on this would be the shear force up minus the shear force down, letting the, and then we can write the shear force down, the shear force at x plus dx, as the shear force at x plus the rate of change of v with respect to x times dx. When we subtract those, the shear force at x cancels out, and we're left with just that rate of change term. Substituting in what we know for the shear force in terms of moment, we can then say that the net force on this little section is equal to negative EI times this rate of this fourth derivative now of transverse position with respect to x, multiplied by dx. So this is the little bit of force on this. It's proportional to the width of the section. We can write the acceleration of this by saying that force is equal to mass times acceleration, or in other words, acceleration is force over mass, and then saying, okay, well, df over dm is df by dx over dm by dx, dividing out the dx from this, and then dividing all that by mu, the mass per unit length, we come up with what's called the dynamic beam equation. This relates the acceleration of a section to the force on it divided by the mass of it in a per length kind of way. Okay, dynamic beam equation is second order in time and fourth order in space. It's basically the same as the regular beam equation, except instead of equating it to 0, we equate it to the second derivative of v with respect to t. You might be wondering in this derivation why we didn't have to consider the moments. There's a little bit of a proof here that you can go through that shows that the moments are, in terms of a net torque of this thing, produce a negligible amount of torque on an infinitely thin section. Suffice it to say that this is the dynamic beam equation. It's not perfect, but we're going to be looking at some of the applications of it, and there's a large range where it's typically valid, generally for quite thin beams, where flexure dominates. Okay, before we get into the details of solving this for some specific cases, let's just look at a solution. And the solution we're going to look at is the cantilever. So the cantilever, we know we've got no displacement at the left end, so v at L at x equals 0 and all time is 0, and no angle at the left end, so v sub x, meaning the partial derivative of v with respect to x, at 0 and all time is 0. And then with no moment on the right hand, that means the second x partial at the right end at L, at x equals L, and all time is 0. No shear force on the right end of a cantilever, the free end, means that the third partial derivative of v with respect to x at L and all time is 0. Now we also need some initial conditions, though, because it's the dynamic beam equation. So what do we need? We're going to say, suppose we release the cantilever from some initial displacement. Releasing it means it has no original velocity. And so these are the two time equations. Even though we write this for the case of solving the whole thing, we're not really going to be dealing with the time component in this course. What I will say, though, is that the solution to this equation ends up being a linear combination of an infinite number of resonant modes. So Vn is the nth resonant mode. Look at this, it's a harmonic part, so all the time dependence is over here, multiplied by a resonant mode shape, something that just depends on position. This turns out to be the mode shape for the cantilever. It looks scary, but you could just type it into Maple and plot what it looks like. It kind of goes almost like a cubic function, basically what you'd expect for a cantilever to bend into the shape of. And beta n is the nth root of this. It's hard to solve this by hand, but if you plot this function, you'll find out that it crosses the axis a number of times because of the cosine function, and where it does that are the roots. So the frequency is related to the beta as well. So the resonant frequency is given by beta n squared, where beta are the roots of these, multiplied by the root of EI over mu. Okay, some examples. What is the fundamental resonant frequency of a cantilever in terms of EI, L, and mu? So what you're going to need to do is find the first root of the beta equation, and then just substitute that into here. Okay, so we can find the first root of that equation, this one, by using the fsolve command in Maple, and there it is. So if you wanted to find another root, you would just constrain the range of fsolve. So here we just said solve it for x, but you could also just give it a specific x range. And it's probably good practice to plot this just to check that you got beta right. I'll leave that as an option for you to do. You can see that this is the first positive beta where this equation has a root. Anyway, this tells us what beta 1L is, because that was the solution to this. So then the beta is equal to this value divided by L. So omega 1 is equal to that same value squared over L squared, root of EI over mu, because omega is equal to beta squared root EI over mu. And that's it. This tells us what the resonant frequency of the first harmonic mode would be if we knew the dimensions of the cantilever, its flexural rigidity, and its mass per unit length. Next example, plot the fundamental mode shape of a cantilever. So the mode shape. Well, that's just this function, and since it's the fundamental mode shape, that means it's the one using the beta that we just solved for. So in terms of L, you can plot what this is. Let's imagine we've got an L equals 1. All right. So here we go, substituting in so we just, if L is equal to 1, then beta is just the solution of this function here. And then we can substitute that into the formula typed out that we have above here. And there it is, fundamental mode shape. What this is telling us is that at 0, we've got no position, no angle, and at the other end, there's no curvature and no third derivative either, meaning no moment and no shear force. Let's put some numbers to this. Suppose we've got this cantilever, so a 1.5 meter cantilever, and it's 10 centimeters thick, so you can picture this. It's got some properties similar to steel, 210 gigapascals, and a Poisson ratio 0.305, density a fair bit less dense than steel. So picture this kind of this beam that's kind of similar to steel but a little bit lighter. What's the resonant frequency of this beam? 1.5 meters long. Okay, substituting in the numbers we found, we can calculate that the resonant frequency is 462 rads per second. All right, there we go. All right, now let's look at the general solution to the dynamic beam equation. This is going to be coming up with that cantilever solution that we were looking at here. To do this in full, you'd use math from the end of 2ZZ3. If you've already taken that, then this might be a review for you. So basically what you do is you assume you can find a separable solution, which is a function of x multiplied by a function of t. Then you substitute that into the partial differential equation, this one, and then separate out into two ordinary differential equations in position and time. Then use the boundary conditions and initial conditions and linearity to solve them. So you find solutions and then form a linear combination of them, because the original differential equation is linear, usually forming an infinite series, so you can satisfy the initial conditions. For our purposes, we don't really need to do all of that. We're going to make things simpler by assuming at the outset that we can find a harmonic separable solution, which is a function of so this mode shape thing multiplied by cos of omega t plus phi. If we substitute this in, then the cosine and the time dependence goes away, and we're left with just solving a fourth order ordinary differential equation. So you can do this in every dynamic beam equation example in this course. All right, so this is an ordinary differential equation in X. And just like you do in Math 2Z03, you solve it by substituting in e to the r x. Even though it's fourth order, don't let that scare you. You find 4 roots, the 4 roots of this function. And then that means the general solution is this. And so far, we didn't do anything to do with the boundary condition. So if you like, you can just jump right to this. And it's an open book test, so by all means start at this line. Although, try it once on your own to make sure you understand where that goes. If not for this course, then for Math 2Z03, because you definitely need to understand that for that course. Anyway, the beta here has been defined in terms of the 4th root here, so 4th root of omega squared mu over EI. You can see this gives our frequency definition from earlier in terms of beta. Now, in order to go further from here, we need to know the initial conditions. For the cantilever boundary conditions, if we apply v at 0 equals 0, then it specifies C1 is negative C3. Then specifying that v prime at 0 is 0 lets us solve for C4. Specifying that v double prime at L equals 0 lets us solve for C2, say. And then we're left with this differential, this equation. We've got one more boundary condition to satisfy, which is v triple prime at L equals 0, the shear equals 0 at the end condition. And for this last one, what we're doing the whole way along when we satisfy these boundary conditions, our goal is to not find the trivial solution. So we don't want to find solutions where v is just equal to 0. Because yes, you could just substitute in v equals 0 to both sides of this, but we're looking for the non-zero ones. Those are going to be the resonant modes, the resonant mode shapes. Okay, so if we want a non-zero solution for v, there's a way to do it from this one, and it's not to set C3 equal to 0 or beta equal to 0. Instead, what we need is, after simplifying things out, we need this term in here to cancel out somehow. Okay, so let's work that out. Doing a little bit of math, simplifying it, simplifying a little bit more. At this last step here, I used the fundamental trig identity, which is cos squared plus sine squared equals 1, and something I'm going to call, just because it sounds kind of cool, the fundamental hypertrig identity, cos squared minus sinh squared is equal to 1. And so we end up with 2 cos of beta L cos beta L plus 2 equals 0, or dividing by 2, the same generating function for the betas that we had earlier. Ta-da! Great. So this lets you solve for beta, and there's an infinite number of roots that correspond to an infinite number of resonant modes. Consequently, from this equation, you can then solve for what the frequencies are. So in summary, the mode shape that we found was this step here before we went and applied the last boundary condition. The C3 is just a free parameter, though. We don't need that. Anything proportional to this would still be the mode shape. So since there's an infinite number of betas corresponding to an infinite number of resonant frequencies and mode shapes and solutions, the general solution to a linear differential equation is just a linear combination of all the independent solutions we found, in this case an infinite number of them, so we'll take a sum of those multiplied by constants. This gives you enough flexibility to satisfy the initial conditions, although we're not really going to do that. Okay, so to conclude this section, I'm going to relate this back to something that you learned about in first year and maybe in high school as well, which is the resonant modes of guitar strings. On the in the Physics 1 E03 formula sheet, you have formulas that give you the speed of a wave on a string that's under tension T and mass per unit length mu, and this is the wave speed. And you know the resonant modes are the ones that fit on the string with nodes at each end, and that's in general sines of pi n by L multiplied by x, where the string goes from 0 to L, giving us this wavelength, 2L over n. And for this wave speed, we can figure out what the frequency is, n pi by L root ft over mu. So then for a thin enough beam with the right boundary conditions, maybe we can reproduce this result. Let's find out. What are the boundary conditions of a guitar string? All right, well, if you think about it, it's kind of wrapped around a post at each end, so that means it can't move in that direction. but the post doesn't apply moment to it, so the angle doesn't matter at the ends, which means there's no displacement or moments at each end. So the 0th and 2nd derivatives are 0. Substitute the boundary conditions into the DE to solve for the resonant modes of the guitar string. This is going to prepare you for question number, at time of speaking anyway, is question number 3 on the sample exams, where you're going to solve for the bridge modes. Not sample exam, rather, sample assignment for today. And the bridge mode boundary conditions, how would you get that? Well, you would substitute in the bridge boundary conditions for now, substitute in these boundary conditions to solve for the resonant modes. Substitute into what? Well, back up here where we went through the full example of this, you substitute them into this equation and solve for C1, 2, 3, and 4. So let's do that. I can even repeat the differential equation solving from the start. Dum-da-da, and there it is. So we'll substitute into here. Try going through this. I mean, I can talk over it. There's nothing really special here. We substitute in one at a time, solve for all the C's, and then at the last step, we have to decide that we don't want V equal to 0 everywhere. So we need to find some way for this equation to be 0 without having without having V at x equal to 0 everywhere. And since beta equals 0 would make it 0 everywhere, we can't have that. Since C2 equals 0 would make it 0 everywhere, we can't have that. So it must be that this sine beta L is equal to 0. Sine beta L can be 0 as long as beta L is n pi, which means beta is n pi by L. And that sets that V hat n at x is, because the sign here is a 0, equal to just sine n pi by L, just like we had for the guitar string earlier. Okay, then determine the resonant frequencies for the guitar string boundary conditions beam. Substituting into what we had above, the omega is beta squared root EI over mu, and this is not the resonant frequencies that we calculated for the guitar string. It's almost the resonant frequencies for the guitar string, but it's not quite. I mean, we've got this term here squared rather than just to the power of 1. So what's the deal here? Well, we've got a different differential equation that we're solving. So it turns out that the guitar string is not exactly the same as the beam, even though we made it thin. For one, there's no tension force anywhere in the equation, in the beam equation that we were solving, and yet that has a lot to do with the resonant frequency of the guitar string. So here's the idea. If you make a guitar string, so if it's thin and then you make it really tight by pulling longitudinally on it, then the longitudinal force has a lot to do with the restoring force. So we didn't include any longitudinal force explicitly in our our flexion equation that we used to derive the dynamic beam equation. Consider what we did for a guitar string in first year, though. So here's an example of a section of a guitar string, and let's find out what the restoring force is as a function of with this set of boundaries, with this set of forces on it. So we've got the axial force here, sigma x. The displacements are kind of exaggerated, so pretend that this is still kind of the x direction, and that's the x direction, but it's moved at a little bit of an angle, theta and theta at x plus dx. So the little bit of force would be sigma times the area. And what's the vertical force from this? So we don't care about the horizontal force, just what's the vertical force. Before we neglected this because we said the moment the bending angle is kind of small, so the longitudinal force is not going to be mattering for the vertical displacement. But now let's consider what it would be. So it's so it's this force, which would be A times this stress times the sine of this angle, minus this force, A times this stress, times the sine of this angle. And if we use this small angle approximation so that sine of theta is basically theta, and we say that the sigma doesn't change much across the beam, so that sigma at x plus dx is ft over a, and so is sigma at x. But the angle maybe is different. Then we come up with the net force being proportional to del v by del x with a second derivative. Applying Newton's second law now to say that the net force is ma, we can come up with the wave equation. You may be familiar with this. It's just a second order in space, second order in time, and this is what leads to the resonant modes and frequencies of a guitar string. So it's not that really the guitar string formula is wrong or the dynamic beam equation are wrong, it's that they're modeling different things. If we apply a lot of axial force by putting a string in tension, then the longitudinal force in the vertical direction as the beam moves becomes more important, and we have to consider that. Either one of the equations are perfectly fine for the domains that they're trying to model. If we want to do a much better job and include all of the equations at once, then this is where finite element methods come in, and we're going to pick up with that on the next lecture.